An understanding of Ohm's law is at the heart of understanding how electric circuits behave. So we're going to explore the behavior of electric circuits in great detail in our next unit. Okay, but for now, we're going to introduce Ohm's law from both a microscopic point of view as well as a macroscopic point of view. And in this slide, we'll take a look at the microscopic version of Ohm's law, which is going to help us explain the relationship between electric fields that get established in media, and the electric current that results from these fields. From the macroscopic point of view, when we look at Ohm's law, we'll see how Ohm's law can help us explain many practical phenomena, from the behavior of electric circuits, to the cause of electric shock, to electric power. So these are all topics that we'll take a look at, in today's presentation. So starting with this microscopic version of Ohm's law, we can state this in words as follows. We can say that the current density at any point in a conductor is directly proportional to the electric field at that point. And said symbolically, or stated symbolically, we can say it like this. We can say that the current density J is equal to this proportionality constant we call sigma, which by name is what we call the conductivity of the medium, times the electric field strength. Notice that both J, the current density, and the electric field are vector quantities, and their direction should be the same. Sigma is a scalar, this proportionality constant, which we'll talk a little more about now. So conductivity, think back to when we talked about the difference between conductors and insulators. We said that conductors, were materials where electric charges could move easily. And in the case of metals, these electric charges, the charge carriers, happen to be electrons. So we see here in this microscopic version of Ohm's law that sigma is that proportionality constant, between the current density and the electric field. We can think of this as a property of the material, of the medium itself, that measures how easily charge carriers can move in response to that electric field. A type of material, a medium that is an excellent conductor, would have a large value of sigma, because this would imply that, you would end up with a lot of current, once that electric field gets established. So we know that when we talked about, resistance and resistivity, and we said that the resistivity was a property of the materials, really in the same way that sigma is a property of materials. It is an intrinsic property. And it turns out that, the resistivity and the conductivity just so happen to be reciprocals of each other, which would make sense. If resistance is really a measure of how much obstruction there is to charge flow, then the conductivity is a quantitative measure of how easily charges can flow in a conducting medium. So how big are these electric fields that get established in current-carrying conductors? Well, let's solve this problem and find out. So here, in this example, we're told that a 2 millimeter diameter copper wire carries a 10 amp current to a household appliance. So these are fairly typical wire dimensions and currents that exist, for typical household appliances. If copper has a conductivity of 6 times 10 to the 7th amps per voltmeter, what is the magnitude of the electric field in the wire? So using Ohm's law is fairly straightforward. We will have to use Ohm's law in combination or in conjunction with the definition of current density here. So let's start here using the definition of current density to calculate what that is, what the magnitude of the current density is, for this current carrying conductor. So by definition, we're talking about the current, the ratio of current to the cross-sectional area of the conducting medium. So we've got 10 amps of current, and we will assume that we have a circular wire cross-section. Make sure that we convert the millimeters to meters. This gives us a value for the current density of about 3.2 million amps per square meter. We can now use Ohm's law, okay, it's in its microscopic form, stated as such, and we can solve this for the electric field. And when we do so here, okay, electric field magnitude or strength is just the magnitude of the current density divided by this, okay, proportionality constant we call conductivity. We found the current density above. Let's plug in the value for the conductivity, which is in an appropriate SI unit. And when we get our answer, we see here, okay, 5.3 times 10 to the minus 2 volts per meter, okay, about 0.53 millivolts per meter. This may seem quite small. And I would say here, note that the electric field is much smaller than the fields that we've been coming across in electrostatic situations. Remember we said that the electric field required for corona discharge, that is to ionize air, is on the order of about 3 million volts. Well, think about it. Okay, because copper is such a good conductor, okay, it has such a high value of sigma, only a very small electric field is needed, okay, to drive a very large current. So you see that in, okay, conducting mediums, as opposed to insulating mediums, these values of electric fields are typically much, much smaller, okay, because of what it means for material to be a good conductor. So in this slide, we'll introduce the macroscopic version of Ohm's law. And to help us see the difference between these two versions, okay, let's recruit our little friend here who tells us that the macroscopic version of Ohm's law makes use of the macroscopic quantities, that is electric potential difference, current, and resistance, which can be measured directly with meters. So we see that in a practical sense, okay, we can make measurements of these quantities much easier than we can a quantity like electric field or current density. We resort to the microscopic quantities, that is electric field, strength, okay, current density, and conductivity, when we want to answer questions about the fundamental electrical properties of materials. So you will see that, okay, the macroscopic version is what you're going to be using almost exclusively, okay, especially when we get to our unit on electric circuits. So let's write a statement of this. And since we understand, okay, very well what these quantities, electric potential difference, current, and resistance means, okay, then understanding Ohm's law is something that, okay, is not going to be new to you. Okay, what Ohm's law tells us is that the current in the conductor is directly proportional to the electric potential difference impressed across the conductor, okay, which would make sense, okay, greater electric potential difference, greater electrical pressure to drive the current, and that the current is inversely proportional to the resistance of the conductor, which also should make sense. Okay, the greater the resistance, the greater the obstruction to charge flow, okay, the lower we would expect the current to be. We can state this nicely in symbolic form as follows. We can say that the electric potential difference impressed between 2 points in a conductor is equal to the electric current between those 2 points, okay, times the resistance of the medium between those 2 points. Now, in the next couple of slides, we'll try to demonstrate Ohm's law. Okay, one directly with some instruments and one using a simulation. And then we'll actually, okay, see how the macroscopic version of Ohm's law can be derived directly from the microscopic version. Notice here that we have a simple electric circuit with a source of voltage, a source of electric potential difference, okay, provided by the battery. And remember, we said that we can think of that electric potential difference, that voltage source, as a measure of electrical pressure that can be used to drive current. Also notice that we have resistance in our circuit in the form of a resistor. We also have an ammeter, which, as we'll find out, is connected in series, which will measure the current, okay, that flows in our circuit. we'll assume that the ammeter has a very low resistance, so it doesn't really contribute much to the resistance of the circuit. First, notice what happens to the current when we increase the voltage by adding more batteries to the circuit. As I said, if voltage can be thought of as a measure of electrical pressure, then we would expect that as we increase the electrical pressure by adding more batteries, we should increase the rate at which charge can flow through our circuit, okay, which amounts to increasing our current. So I can't control the speed with which the simulation takes place, okay, but you will see these factors here. Now, the next factor, okay, aside from increasing the number of batteries from 1 to 3, causing an increase in current, we can also increase the number of resistors from 1 to 3. And as we said previously, if resistance is a measure of obstruction to charge flow, okay, then we would expect that the greater the circuit resistance, the greater the obstruction of charge flow, okay, the lower the rate at which charge can flow in the circuit. That would mean the lower the current in the circuit. And that's exactly what this simulation shows. Again, I can't really control the speed with which this happens. I will attempt to show this to you in real time with real equipment, okay, in the next slide.
We're going to take a look at Ohm's law. And Ohm's law tells us that there are really two factors that affect the electric current in a circuit. One of those factors being the voltage impressed across your circuit. Remember, we think of voltage as an electrical pressure difference, and the second being the resistance of the circuit. Now, if you take a look at this setup, we have a complete circuit. We have our source of voltage represented with this battery eliminator here. We can vary the voltage and see how that affects the current. And if we trace the circuit, we'll see, starting with the negative terminal, that electrons can flow from the negative terminal through this black wire. They can flow through this device, which is an ammeter, an analog ammeter, which will measure the current in the circuit. They can flow out the other side of the ammeter through this red wire. They can come here, and then they can flow through this piece of resistive paper, which is going to function as our wire. It has more resistance than a typical wire. So we can not only get a measurable resistance, but we can change the resistance by changing the contact point with the wire. So if we let this end of our alligator clip move closer to the other end, we can lower the resistance. And anyways, so these electrons will flow out the other side of that piece of conductive paper to the positive terminal of the battery eliminator. So we have a complete circuit. So let's start by taking a look at the effect of voltage on current. You'll notice here, looking at the DMM, that we have a certain voltage and we have a certain current. Notice what happens as I increase the voltage. As I increase that voltage by turning the dial, I'm going to increase the electrical pressure across the ends of the circuit, therefore increasing the current. So here goes. Increasing that voltage, notice that the current increases as well. Okay, now we've pegged our meter, we've maxed out. All right, so we see there's a direct relationship between voltage and current. Let me go back and let's now take a look at the effect of resistance on current. Right now, we have one end of our lead at one end of this piece of conductive paper, and we have a certain amount of resistance and a certain amount of current in here. Okay, notice what happens as we lower the resistance. As I slide this lead closer to the other lead, so our wire shortens, our piece of conductive paper shortens. Notice what happens to the current. Less resistance should provide more current, more charge to flow through this piece of conductive paper. So here we go. As I slide this other end, notice what is happening to the current in our circuit. I'm going to have to break it for a second here. Let's get down real short here. notice that now we've pegged out the meter again. So we see this inverse relationship between current and resistance. As the resistance goes down, the current goes up for the same voltage, the same electrical pressure difference across the ends of our wire.
All right, so in this slide we will see how the macroscopic version of Ohm's law can be derived, okay, naturally from the microscopic version. So as long as we have an ohmic conductor, and by the way, not all materials are ohmic. In other words, not all materials obey Ohm's law. Most metals do, but not all metals. In fact, if you look at the very thin tungsten filament of a light bulb, okay, we would classify that as a non-ohmic conductor because it doesn't obey Ohm's law. Also, when you look at your semiconductors are also non-ohmic. But many materials are what we can consider ohmic in that they obey Ohm's law, and most metals do. So, if we consider a segment of straight wire of length L and cross-sectional area A, as you see in the diagram here, okay, so piece of conductor, piece of wire, okay, length L, cross-sectional area A, then we can say that if there is a potential difference, delta V, maintained across the wire, okay, pressed across the ends of the wire, then according to our microscopic understanding of Ohm's law, an electric field and therefore current I is established within the conducting medium itself, within the wire. And you see here I'm showing the electric field established. Remember we said that for a uniform electric field, and this is one of the assumptions we make with Ohm's law, okay, we have an expression from our unit on electric potential difference. In electric potential, we showed that for a uniform field, okay, the electric potential difference goes like the field strength, okay, times, in this case, the length of our wire, if we're talking about the potential difference impressed across the ends of the wire. Okay, so for any 2 points, if the field is uniform, we can say the potential difference between those 2 points is equal to the electric field established, okay, between those 2 points times the distance between those 2 points. Okay, our 2 points here are just 2 ends of a wire. From here, we can substitute this into our microscopic version of Ohm's law, which says this: current density equals conductivity times electric field strength. I'm looking at the magnitude of these quantities only. And by the definition of current density, that is just the current per area, and we substitute our version for electric field, we substitute, okay, these macroscopic quantities, that is delta V and L, which are measurable. And from here, okay, we're just going to solve for delta V. Just do a little bit of algebra here. And you'll notice on the right-hand side, we have this factor here, L divided by sigma A. Remember, the conductivity and the resistivity are simply reciprocals of each other. So if we now make that substitution, right, in terms of the resistivity instead of conductivity, okay, this should look very familiar to you. Okay, when we talked about resistance, the resistance in a conductor, we came up with this expression that the resistance went like the resistivity times the length of the conductor divided by the cross-sectional area. So this right here is nothing more than the resistance of the conductor. When we make that substitution, we end up with our macroscopic version of Ohm's law. So let's take a look at an example of applying Ohm's law. We'll consider a very simple device, the original lie detector. Now, I'll admit that in today's world, there are many different types of lie detectors. And as Homer Simpson is illustrating in the cartoon, okay, the most common type of lie detector today uses heart rate, okay, to measure truth telling, or, okay, as Stephen Colbert nicely puts it, truthiness. But the original lie detector looks something like what you see illustrated in the right-hand portion of your screen. okay, where your body becomes part of a simple circuit. In this way, charge can flow through part of your body, okay, usually your finger, and a sensitive meter, really an ammeter, will show the current that exists when a small voltage is applied. So how does this technique indicate that a person is lying? Well, with a constant voltage source provided by a battery or some other similar device, and an ammeter that can accurately measure the current, okay, we have to think about what happens when, okay, a person lies. Okay, when someone lies, the autonomic nervous system causes increased perspiration, okay, increased skin wetness. And this greatly lowers the body resistance. And according to Ohm's law, okay, when the body resistance goes down, the current goes up, right? There's an inverse relationship between resistance and current. And as that current goes up, that needle is going to jump, indicating that the person is lying. So you see that this very simple technology functions as a direct result of Ohm's law. Now it turns out that not all materials obey Ohm's law. Materials that obey Ohm's law are what we call ohmic materials, okay, or ohmic conductors. Materials that don't obey Ohm's law are what we call non-ohmic materials or non-ohmic conductors. So to contrast these two different classes of materials, okay, we'll start and say that an ohmic conductor is a material, okay, for which the conductivity is independent of the electric field. And what that means then is that, okay, if the conductivity is independent of the field that gets established in the material, okay, that would be a material where the resistance of that material is constant. And like I said, this is a material that would obey Ohm's law. When we look at a graph of the potential difference across a piece of this material versus the current in the material, okay, what we find out is that, well, according to Ohm's law, that resistance, if the resistance is constant, that would tell you that in this graph, the slope of the line is constant, that it would be a linear graph because constant resistance means constant slope, right? When you look at the graph of, okay, potential difference versus current, then that would indicate, okay, the resistance is simply the slope of that graph. It turns out that most metals are ohmic, okay? They obey Ohm's law. A non-ohmic conductor, a non-ohmic material by contrast, would be a material where the conductivity does depend on the electric field, in which case, okay, the resistance is not constant for that material. As we said, this would be a material for which Ohm's law is not obeyed. So there's not simply one type of non-ohmic conductor. If we look at a graph of, okay, potential difference versus current, we know it's not going to be linear, okay, but some graphs will look like this, and I'll give you an example. If you look at the tungsten filament of an incandescent bulb, okay, and you look at this relationship of, okay, the voltage versus a current, you'll see that it follows a trend that looks like this. When you look at certain types of semiconductors, for example, okay, certain types of diodes, this depends upon the way that they are combined. Okay, you can get graphs that look like this. Okay, so, but in either case, we see that the resistance, which would represent the slope of the graph, changes, okay, with current and potential difference. So like we said, semiconductors are the classic example of non-ohmic materials. Let's now turn to the topic of electric shock. And as we'll see, understanding electric shock really amounts to understanding Ohm's law. Who knows? Okay, what you learn about in this slide could potentially one day save your life. Okay, let's start by asking the very fundamental question, what is it that causes electric shock? Well, very simply stated, electric shock is the direct result of current that exists in your body. So that kind of begs the follow-up question, why is having current through your body so bad? What is it that actually causes the harm to your body? Okay, well, there's really two causes, really two sources of this harm. The first being that when charge moves through a material, okay, the resistance leads to frictional heating. And when heat is generated, that heat generated kills cells, okay, damages cell tissue. Okay, but perhaps the bigger cause of the bodily harm is this. Your body is a huge network of electric circuits, and too much current can disrupt the electrical signals in your brain and your heart, okay, that cause both of them to function properly. So this is the secondary, but perhaps more important problem with electric shock. It really depends, okay, where the current exists in your body. Okay, why is electric shock lethal? When is it lethal? Typically, electric shock is lethal, okay, when the current goes through your heart. Certainly, if you're killing some cells in your arm, for example, it may be painful to your arm, but usually not lethal. Okay, you'll survive that. But believe it or not, it takes only about 0.05 amps of current through your heart, okay, to actually prove fatal. So that is not a large current, and that is, okay, the biggest source of the problem. So, if you can have a large current that flows from one hand, okay, through the side of your body down your leg to the ground, and while it will prove painful, okay, destroy cells, okay, destroy tissue, usually you'll survive that. Okay, but only 0.05 amps of current through your heart. Okay, that is not a lot of current, and that is where the problem results. So, if we ask the question, what are shock-inducing situations? That is, what are the scenarios that lead to shock? Well, certainly when we look at Ohm's law and see what Ohm's law tells us, any situation, any scenario where there is a large potential difference across your body, that puts you in at high risk of having a large current through your body. Certainly, you know that the high voltage lines that you see running along the canal banks controlled by MID, well, no surprise there that several 100,000 volts would certainly lead to a situation where a large current could exist in your body. But as you well know, okay, many people in the United States die every year from simple, okay, household electrocutions from, okay, the 110 volt outlets that you'll find in U.S. households. So it doesn't have to be huge potential differences to prove lethal. And that's where the second condition comes into play, and that is, okay, think about what Ohm's law says, this inverse relationship between current and resistance. So when the resistance of the body is very low, okay, that leads to situations with high currents. And the human body is pretty amazing. When you think about it, what is inside of your body is an electrolytic solution. It is a very good conductor. Okay, water and salt. Okay, what is it that prevents that water and salt, the inside of your body, being an excellent conductor from actually having a large current in it from external sources? Well, it's really your skin. That is the protection. Turns out when your skin is dry, it can have a resistance of 500,000 ohms. But when your skin is wet, okay, like in a situation after you've taken a shower, that skin resistance can change by many orders of magnitude and can, go as low as 100 ohms, a very low resistance. So wet skin, okay, any situation where your skin is wet, that favors electric shock. And while it may seem surprising, if you think about household electrocutions, most of your appliances would be in a garage or a kitchen, yet most household electrocutions take place in the bathroom. Think about it, it's a perfect storm. You get out of the shower, you're stepping on a tile floor, which is a much better conductor than a carpeted floor, or a wooden floor, and you don't have any shoes on, right? The rubber soles of your shoes also provide, an excellent insulator between your body and the ground. So you're in a situation, wet skin, low resistance, connected to a good floor conductor with nothing really between your skin and the floor in the way of insulation, okay, you are putting yourself in a shock-induced situation where a faulty appliance can easily kill you. So we'll take a look in the next slide, what I call the human battery. We'll take a look at really current that can get generated through the body and the effect of wet skin, okay, how the lowered skin resistance can increase current.
So here we have what I would call a human battery. I'm going to really get into the circuit here, become a part of the circuit. As with any battery though, we have two different types of metals, each metal with a different tendency to gain and lose electrons. This is a piece of aluminum over here, and this is a piece of copper. And it turns out that aluminum has a much greater tendency to lose electrons than copper. So that means that this aluminum sheet can produce a higher electrical pressure than the copper sheet. And if we provide a pathway for those electrons to flow, that is via me, since I'm a pretty good electrical conductor, we will get electrons to flow from this aluminum through me onto the copper sheet. And we'll be able to see this flow of electrons because we've connected an ammeter here. So let me go ahead and put my hands on here and complete the circuit, and let's take a look at this flow of electrons from the aluminum to the copper. You will probably notice here I've now broken the circuit. Let me put my hands back down. You'll see the current in the ammeter. Okay. Now, in order that we don't have electrons building up on the copper, it's necessary, as with any battery, for positive ions, and that is sodium ions in my body, to now flow to the copper to neutralize those electrons so we don't build up charge on any sheet. What I'd like you to do is to now notice what would happen if I soak my hands in some salt water to make them an even better electrical conductor. You will see that when we complete the circuit, we're going to get a lot more current flowing through this battery as I become a better conductor. So here we go. Let me now place my hands on the sheets, okay, and you will notice what happens to the electric current. I can't see it, but there should be a whole lot more current flowing in this battery now that I've become a better conductor. So once again, a battery, two dissimilar pieces of metal with different tendencies to lose electrons, and we can get those electrons to transfer from one piece of metal to the other and capitalize on that flow of charge.
In this slide, we'll consider what I call the amateur mechanic, and this is, we'll take a look at a specific example to some of these shock-inducing situations that I alluded to in the previous slide. So if you're the sort of person who likes to mess around underneath the hood of a car, okay, well, and you don't completely know what you're doing, there's a very simple rule to employ, okay, for those of you that okay, are not expert mechanics. And the rule is this, okay, to avoid electrocution, keep one hand behind your back at all times. So remember that you've got a very high capacitance capacitor in your car, okay, in order for that starter motor to provide the power surge to make your engine rotate from a state of rest, to overcome its huge amount of inertia. Should you become a part of that starter circuit, okay, well, you run the risk of that capacitor discharging through your body. So the basic rule of keeping one hand behind your back is a good one. Should you inadvertently become a part of that high voltage circuit, okay, so that a large potential difference would exist across your body, okay, that is from the contact point through one of your hands to the ground, Well, keeping one hand behind your back, charge will take the path of least resistance, okay, and moving from that high potential source, which, like we said, would be one hand, to the low potential, which would be the ground. So in that case, charge will flow probably down your arm, through one side of your body and out your leg. And while that shortest path will certainly prove painful, okay, it probably will not prove fatal. Okay, but think about what would happen if you actually didn't have that other hand behind your back and your one hand came in contact with that, okay, high electric potential source, and let's say the other hand happened to be resting on the metal frame of your car. Well, now that shortest path to ground, okay, through your car would be from one hand through your heart and out the other hand. And that's where the problem happens, right? You do not want that charge to flow from one hand to the other hand, because in that case, it will flow through your heart and could prove fatal. So the following story is a true story involving electrolytic solutions and Ohm's law, of course, and the names have been changed to protect the innocent. So this is a story of the early retirement of poor Richard, the utility worker. So Richard was a worker for an electric company. I believe it was SMUD in Southern California, and he was doing some routine maintenance on a high voltage power line. He was working alone, and he hoisted himself near the power line by means of a cherry picker. Now, for some reason, this cherry picker became unmoored. Okay, it suddenly moved from its rest position, okay, maybe due to a faulty brake, resulting in Richard and the cage of the cherry picker that he was in, okay, bringing them both into contact with this high voltage power line. Now, Richard, okay, even though he was now at an extremely high electric potential, well, he was doing just fine. Why? Well, because there was no electric potential difference across his body, okay, mostly due to the insulated tires of the cherry picker. And when you think about it, even if those cherry picker tires weren't perfectly insulated, okay, the electric potential difference, okay, between the line and the ground, the fact that Richard was in this metal cage, where metal is a much better conductor than human being, okay, most of the charge taking the path of least resistance, okay, would have flowed through the metal cage, okay, rather than through Richard himself. So he was safe for a couple of reasons. So once this contact was made, Richard radioed for help, okay, but unfortunately for him, his call took place after lunch, and poor Richard, okay, had been known to have a few too many beers with his cronies during his lunch hours. So as he was waiting for help to arrive, nature began to, okay, beckon. Nature began to call, and finally, okay, not being able to take it anymore, Richard succumbed to these urgent beckonings. Okay, he's unzipped his pants and he began to urinate from the cage, okay, the cage of the cherry picker. And unfortunately, okay, that was his last great, okay, or not so great act in life. So, okay, can you imagine what happened to Richard and why? Well, let's suppose, just for the sake of argument, that the electric potential of that high voltage line was 20,000 volts, okay, which was really no problem so long as his entire body was an electric potential of 20,000 volts. Okay, but remember, urine is an excellent conductor. Okay, it is an electrolytic solution consisting of water and a lot of dissolved salts. So now, okay, with this urine stream connecting his body to the ground, okay, okay, there was now a 20,000 volt electric potential difference across his body, okay, providing a pathway for charge to flow through him, okay, from high electric potential to low electric potential. So, okay, bottom line, if you should ever find yourself in this situation in life, don't follow in the footsteps of poor Richard. So this last example involving Ohm's law doesn't really involve electric shock per se, but is an interesting example nonetheless. And this is the true historical example of the Hindenburg disaster. Okay, the Hindenburg was a giant blimp, okay, a dirigible, a Zeppelin. And in 1937, okay, this disaster happened while the Hindenburg was trying to land in a port in New Jersey. So I'll show you some pictures here. There is, okay, this giant blimp which, okay, transported people from place to place. Okay, here you see it flying in the air. It looks kind of like the precursor of the Goodyear blimp. And anyways, okay, I'll show you a picture of what happened on that fateful day, okay, May 6, 1937. Okay, the Hindenburg was destroyed, okay, while it was attempting to land. And if we look at the fire that resulted, okay, it turns out it was a direct result of Ohm's law and really a lack of understanding, okay, of the effects of Ohm's law, because this disaster was entirely preventable. So let's take a look at what happened. Well, when the Hindenburg was preparing to land, okay, the handling ropes were let down to the ground crew. As I've tried to illustrate in this very badly drawn design, you see that these handling ropes are attached to the metal frame, okay, for which the skin, which was inside of the skin of the blimp itself. And what happened is these handling ropes, it was raining, they became wet, okay, and were thus able to conduct an electric current. So in this condition, the ropes essentially grounded the metal framework of the Zeppelin, okay, to which they were attached to. Okay, the ropes formed the conducting pathway to ground. So now, okay, the inside frame of the blimp was now at the same electric potential as the ground. Okay, well, this should have grounded the fabric of the Zeppelin as well. Okay, yet the Hindenburg was the first of its kind to have the fabric painted with a sealant of large electrical resistivity. Okay, thus, the fabric remained at the electric potential of the atmosphere, okay, at the Zeppelin's altitude of about 43 meters. So due to the rainstorm, the atmospheric potential was large, okay, the electric field was large there in comparison to the ground. Okay, well, to make matters worse, the handling ropes apparently ruptured one of the hydrogen cells, okay, in the balloon, okay, in the blimp, and released hydrogen, okay, between the cell and the Zeppelin's outer fabric, and this was noted as the rippling of the fabric. Okay, when they retold the story, many of the surviving passengers, I think there was, 35 to 40 fatalities, and many of the surviving passengers talked about, okay, this rippling effect of the fabric due to the rupturing of the hydrogen. Now, certainly, okay, had they used helium rather than hydrogen, that would have prevented this disaster as well, because hydrogen is extremely combustible, okay, extremely flammable. So now we have a very dangerous situation. Okay, the fabric was wet with conducting rainwater and was at a potential that was very different, okay, from that of the Zeppelin's framework and ground. Okay, and this large potential difference between the outer fabric and the metal framework caused charge to flow, okay, along the wet fabric at the high potential and then spark, okay, through the released hydrogen, okay, to the metal framework, which was at a much lower electric potential, okay, the potential of the ground. And this spark ignited the hydrogen in the process. And as the little video clip nicely illustrates, you can see the effect of that. So had the Hindenburg been given sealant of a lower resistivity, okay, no potential difference would have resulted and the disaster would have been averted. And similarly, had they actually used the inert gas helium rather than hydrogen, that also would have prevented this, this deadly disaster. So what remains in this presentation, we're going to talk about electric power. Now we're going to conduct an entire unit on electric circuits, but remember that power in general is simply the rate at which work is done or the rate at which energy is transformed, okay, or converted from one form into another. When we talk about electric power, we're really talking about electrical energy, okay, that is being converted to other forms of energy via some type of circuit. And when we talk about electrical energy, well, we really have two forms. We have the potential energy that is provided by, okay, the source of electric potential, okay, whether it be a generator or a battery. But that electric potential energy, when it is hooked up to a circuit, okay, causes the flow of electric charge, okay, typically electrons. And we can think of that electrical energy as a measure of kinetic energy, right? It's a microscopic form of kinetic energy as those electrons are moving, let's say, in one direction in a DC circuit or are moving back and forth in the case of an AC circuit. So, okay, we end up with moving electrons. Those moving electrons possess kinetic energy. And those moving electrons, that kinetic energy can then be converted to other forms. So in this slide, we'll just take a look at some typical examples here. As you well know, that electrical energy, those moving electrons, can be used to power the electrical lighting in your house, whether in the form of incandescent bulbs, okay, fluorescent lighting, okay, LEDs, whatever. Very commonly, electrical energy is converted into heat or thermal energy. Like in the case of making toast in a toaster, okay, of using an electric range, right? If it's, okay, when we're talking about a gas range, of an electric range, the kinetic energy of those moving electrons ends up in the form of thermal energy, okay? Or, even an electric coffee maker, the process of making coffee, okay? That involves a heating element to heat water. Very often electrical energy is converted into mechanical energy in a circuit. Okay, any kind of device where there's an electric motor, where you have a fan, for example, or a blender, okay, or in the case of an electric drill. So these are all examples where electrical energy gets converted into, okay, mechanical energy, which we can think of as a form of macroscopic kinetic energy. So just given this, we will now talk about, okay, the rate at which the electrical energy gets converted into these forms, okay, via the various types of circuits that we come across in modern society. So we're now going to turn our attention to the topic of electric power. That is the rate at which electrical energy gets converted into other more useful forms of energy. So we will consider a very simple circuit consisting of a source of voltage or electric potential difference, which gets impressed across a resistor having a resistance R, okay, driving a current through the resistor. So we can think of this as in the previous slide, that resistor could be a heating element, okay, or it could represent the filament of an incandescent bulb, okay, which is providing light. So when we take a look at the energy conversions in the circuit and we apply the law of conservation of energy, we can think about this as follows. We can say that, okay, the electric potential energy that is lost as charge, okay, as a charge carrier, typically an electron, moves from one terminal of that voltage source to the other, okay, as it falls through that potential difference, that loss of potential energy, okay, gets converted into thermal energy. Okay, that would be the heat that is dissipated by this resistor. So I realize that this is only one form of energy, but it is a very common one, okay, that we see in all circuits. The amount of electric potential energy that is lost by a charge carrier, let's say Q, okay, we know from our unit on electric potential, we can say that, okay, from our definition of electric potential energy and potential energy difference, okay, delta U, that difference in electric potential energy, is equal to the charge of the charge carrier times the electric potential difference, right? This is the definition of electric potential difference. So in the next slide, we'll take a look at, okay, from this, deriving some expressions for, okay, the electric power associated with, okay, charge moving through the circuit. All right, so now that we've talked about how to measure the electric potential energy that, okay, gets lost as a charge carrier moves through the simple circuit, okay, we can now go from energy to power, okay, remembering that, okay, electric power is simply the rate at which this electric potential energy gets converted into other forms. And we're looking at the simple case, a simple circuit involving a resistor, okay, allowing that loss of electric potential energy to get converted into thermal energy or heat. What we'll find out, though, is that these expressions we've derived for electric power are actually more general. Okay, so even when we talk about electrical energy getting converted to other forms than just heat, okay, these results that we derive in this slide will still apply. So, but starting with the power that is dissipated in heating the resistor, okay, in the simple circuit we're looking at here. First, we're going to derive an expression for electric power as a function of current and voltage. And look, from our definition, if power is the rate at which electric potential energy gets converted, okay, that would be a measure of okay, electric potential energy, delta U, divided by time. Remember, a rate is always some quantity divided by time. This expression is what we derived on the last slide. This comes from our definition of electric potential difference, right? Q delta V represents a loss of potential energy, okay, for that amount of charge as it makes its way from one terminal of the battery to the other, okay, divided by time. And when you look at this, you say, oh, charge divided by time. Well, that's just a measure of electric current. So here we have our first expression for electric power. Okay, the electric power goes like the current times the electric potential difference, okay, for your circuit, okay, which is driving the charge through your circuit. And I say here that although this expression for power is derived for a specific case, that is a conversion of electric potential energy into thermal energy, it is valid anytime electrical energy is converted to any other form. Okay, so this is generally true, okay, for other circuits. You know, whether it's a resistor there, whether that source of electric potential difference is, okay, operating an electric motor, okay, or whatever. We can now, using Ohm's law, write an expression for electric power in terms of current and resistance. So starting with this expression we derived, okay, remembering that Ohm's law says that this potential difference goes like current times resistance, and making that substitution, we can now write power goes like current times resistance, okay, or said electric power goes like I squared the current squared times the circuit resistance. So obviously this expression here is going to apply when you have a measurable resistance in your circuit. We can again do something similar here. We can derive an expression for power, okay, as a function of voltage and resistance, okay, once again using Ohm's law but substituting differently here. So we see, starting with our expression power equals current times voltage, let's now make this substitution for current, getting rid of current, and we see that we have power, okay, measured as the square of potential difference divided by resistance. So really three expressions for electric power. The second expression here, I squared R, is sometimes referred to as the I squared R power loss, and this specifically applies to, okay, the loss of electrical energy, the rate at which electrical energy is lost, okay, due to thermal energy, okay, due to heating as that charge moves through the circuit. So as we'll see, anytime you have, okay, electrical energy being transferred through conducting media, through wires basically, you have this I squared R power loss due to frictional heating. And this is unavoidable. Certainly the longer the conductor, okay, the more resistance exists, the more I squared R power loss you're going to have. All right, I don't think that you're going to learn anything new in this slide. In this slide, we're simply going to review the units for electric power. And I'll say this, that the units for electric power are the same as the units for mechanical power when the concept of power was introduced in your mechanics course. So this should all be very familiar to you. The SI unit, of course, is the watt, right? Okay. When 1 joule of energy is transformed, okay, in 1 second, now we're talking about a rate of 1 watt of electrical energy conversion. The British engineering unit, which we still come across occasionally, is the horsepower. We see this less commonly used when we're talking about electrical power, but you should still be familiar with that unit. A horsepower, turns out, is 550 feet-pounds per second. And the conversion there between horsepower and watts, just remember that big old jet airliner, right? 1 horsepower being about 746 watts. And if you take a look at Bongo over here, I just want to point this out, okay, that when we talk about measuring electric power in kilowatts, a common unit that you will see is a kilowatt hour. And just remember that a kilowatt times an hour, that is not a unit of power. Okay, it is a unit of energy, right? If power is a measure of energy per time, then when you take power multiplied by a time unit, you get a measure of energy. And so when you pay an electrical bill, okay, for MID, TID, you will probably be charged for not the rate at which you use electrical energy, but for the total amount of electrical energy you use, and that unit will probably be, okay, in kilowatt hours. So we'll finish up today by taking a look at a couple of examples involving electric power. And this first example here, we're told that the voltage in a typical household wiring is 120 volts. Okay, how much current does a 60-watt light bulb draw? Okay, and then what is the bulb's resistance under these conditions? Well, we can use our power formula expressed in terms of current and voltage to directly calculate the current here. Okay, the ratio of power to, okay, potential difference. So 60 watts divided by 120 volts gives us a 0.5 amp current through the bulb. And we can now, once the current is known, we can use Ohm's law to actually calculate the resistance. So according to Ohm's law, that resistance is just the ratio of the voltage to current. Okay, 120 volts over, okay, 0.5 amps. Okay, gives us a resistance of 240 ohms. Just want to point out that as we alluded to previously, the incandescent light bulb is an example of a non-ohmic conductor. So what we calculate here is slightly misleading. Okay, a non-ohmic conductor, you remember, is a conductor whose resistance is not constant, okay, for a given voltage suppressed across it. Okay, and therefore a conductor that does not obey Ohm's law. When the light bulb is turned on, okay, it undergoes a huge temperature increase. Remember that bulb filament is designed to be very thin, okay, to provide a high resistance, okay, so that the temperature increases enough to actually emit light. And that huge temperature change in that very thin filament will then cause the resistance to increase as well. So during that heating process especially, okay, there's a huge change in resistance of that filament, in which case, you know, we are calculating, you know, here a single value for resistance, which I'm saying is a little bit misleading. Okay, maybe we think of that as an average value, but okay, that resistance is going to fluctuate, okay, with the change in temperature. So this last problem we'll take a look at today, involving this concept of electric power, has to do with how electric power gets transmitted in industrialized societies like ours. So why is it that electrical power transmission, okay, from the power plant to your home is accomplished at high voltages and low currents rather than at low voltages and high currents? I mean, we derive this power formula. It says that power equals current times potential difference. So why shouldn't these two scenarios be equivalent? In other words, transmitting power at a high current, low voltage could give you the same power output, okay, as transmitting the power at a low current, high voltage. So why is it that we do the way power is actually transmitted, okay, is in the form of high voltage, low current? Well, to understand this, remember that we talked about this I squared R power loss when we derived these expressions for electric power. And we said that the I squared R power loss, okay, has to do with the wasted electrical energy that gets converted into heat, okay, due to the transmission of electrical power. And when you think about it, very often where the source of the power is generated, okay, at the power plant where the generator is, very often the source of the power may be quite far away from the intended target of the power, which would be the residential portion of the city where the homes are. So what happens then is, due to the long distances of transmission, okay, typically through copper wires, you can see here the problem. Looking at the formula here, okay, I squared R, okay, to transmit electrical power at a high current, well, true, you are squaring a large number, okay, if the current is high, but then you are multiplying it by a large value of resistance. Think about it, these copper wires can be, you know, many kilometers long, and when this is the case, the I squared R power loss, okay, by the time that power goes from the power plant to the homes, okay, through many miles of copper wires, very often about 40% of that electrical energy, okay, can be wasted in the form of thermal heating. So what's the advantage of using the high voltage, low current concept to transmit power? Well, when you look at this formula over here, you see, yeah, a high voltage, you're also squaring the voltage, so it doesn't seem like you're gaining anything, okay, versus squaring the current, right? Current, if the current is large or the voltage is large, you're still getting a big number in your numerator here. But take a look at the denominator. If the resistance is typically large due to the, you know, many kilometers of copper wire, okay, in this case here, you're dividing by a large number, which means you're going to get much less power loss to thermal heating than you would by taking your current squared, a large number, and multiplying by a large value of resistance. So when we transmit power in this country, it is in the form of AC, okay, alternating current. And the reason for this is that transmitting power via AC as opposed to DC allows you to use a device called a transformer, We're going to talk in much greater detail about transformers when we talk about electromagnetic induction. But suffice it to say for now that the advantage of the transformer is that you can step up or step down voltages. So typically, the power is produced at high voltage, low current. Okay, it is transmitted at that high voltage, low current from the source, from the power plant, okay, to the many kilometers away where the residences are, and then the power via a transformer, okay, that voltage is stepped down, okay, so that, okay, the voltage will go down, the current will go up, and we have avoided, okay, the huge I squared R power losses in the transmission process.